Hey guys, chapter 5. This is the last section, chapter 5, counting techniques. And here we have, so the fixed price dinner at a restaurant provides the following choices. So we have appetizer, you could either get a soup or a salad. Entree, you could either get baked fish, broiled beef patty, baby beef liver, or roast beef au jus. And dessert, we either have ice cream or cheesecake. How many different meals can be ordered? Okay, so we have 3 different things, right? Appetizer, entree, and dessert. For appetizer, we have 2 different possibilities. For entree, we have 1, 2, 3, 4 different possibilities. And for dessert, we have 2 different possibilities. So here we could actually look at each and every single one. So for appetizer, we could either have a soup or a salad. And just because it's a little bit easier, let's do dessert next, because we could have 2 different desserts. So we either have ice cream or cheesecake. And then from each of these, we have 4 different options for our entree. So we have 1, 2, 3, 4. 1, 2, 3, 4 for this one. 1, 2, 3, 4 here. 1, 2, 3, 4 for that one as well. And this one is, we'll say this one's the C for chicken. This is the beef patty. This is the baby livers. And the last one is the roast beef. So C, B, L, R, C, B, L, R, and C, B, L, R. And now from here, what we have are a bunch of different possibilities. So we have a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. So we have a total of 16 different possibilities. But now, is it going to be like this all the time? Like, is there an easier way to find these different possibilities? So again, we had 2 choices for appetizer, 2 choices for entree, 2 choices for dessert. Here are all the different possibilities. I did it a little bit differently than I did. I just found the other way a little bit easier. And if you look at all of these, so for each choice of appetizer, we have 4 choices for entree. For each choice of these, 2 times 4 gives us 8 choices. There are 2 choices for dessert, which gave us a total of 16. So actually, we only have to multiply these different possibilities. So we had 2 choices for appetizer, 4 choices for entree, 2 choices for dessert, multiply all those together, and we got 16. So if a task consists of a sequence of choices in which there are P selections for the first choice, Q selections for the second choice, R selections for the third choice, and so on, we would just multiply those. And it would find then the task of making these selections can be done by multiplying or finding the product of those. And it would be that many number of different ways. So looking at this one, International Air Transportation Association assigns 3-letter codes to represent air locations. For example, the code for Fort Lauderdale International Airport is FLL. How many different ways? Another one is LAX, the airport in Los Angeles, LAX. How many different airport codes are possible? So here it's 3-letter codes. So 1, 2, 3. They didn't put any restrictions on any of this. So we have 26 different letters that we could choose for the first, 26 for the second, and 26 for the third. So it'd be 26 times 26 times 26. or we could even say 26 to the power 3. Taking it over here, we have 26 raised to the power 3. Got to put the equal sign. And that's how many different possibilities we have. So there's 17,576 different ways that we could select these 3 letters. $17,576, and different airport codes are possible. All right, so now looking at this problem, 3 members from a 14-member committee are to be randomly selected to serve as chair, vice chair, and secretary. The first person selected is the chair, second person selected is the vice chair, third person selected is the secretary. How many different committee structures are possible? So again, we have 14 members. And we have 1, 2, 3 different chairs. So there is not one person that could serve as all 3 different chairs. So with the very first person, we would have 14, but one person would be selected for that position. So now we would have 1 less for the next one. So this one would be 13. We would have 1 less than that for the next position. So that would be 12. So 14 times 13 times 12 is the number that we're looking for here. So 14 equals 14 times 13 times 12 and 2,184. And that's it there. So 2,184 different committee structures are possible with 14 different people. All right, so now that brings us to factorials. So if n is greater than 0, or n greater than 0 is an integer, the factorial symbol, which just looks like an exclamation point. Factorial symbol is defined as follows. So we have n, and we're subtracting 1 from that. So n times n minus 1 times 3 times 2 times 1. So just to show you an actual value, 5 factorial, we would start with that number 5, and we would just keep going down until we hit 1. So 5 times 4 times 3 times 2 times 1. And if we were to actually input that number, we have a command here. So equals factorial. And the number here is going to be 5. And that's 120. But you could also get that number from 5 times 4 times 3 times 2 times 1. And that's how it is. So again, this one is factorial or fact. And then whatever number you were looking for. Also 0 factorial is equal to 1. And 1 factorial is equal to 1. All right, so you've just been hired as a book representative for Pearson Education. On your first day, you must travel to 7 schools to introduce yourself. How many different routes are possible? So we could do it the long way, choosing 7, 1, 2, 3, 4, 5, 6, 7. There's 7 choices for that first one. Since we already traveled to 1 place there, we would have 1 less. Since we've traveled to 2 places, we would have 2 less, and we would just keep going down. So that would be 7 times 6 times 5 times 4 times 3 times 2 times 1. But here we kind of have something to help us out with that, right? We have 7 factorial. So we're going to go over to Pearson. So remember, this is equals fact. So fact for factorial. And the number here we're looking for is 7. So 7 factorial. And now that we found that number, we know that there's 5,040 different ways to travel to those 7 different destinations. So they called it schools A through F, or I'm sorry, A through G. And so for the first, second, third, fourth, fifth, sixth. So there are 7 different choices for school A. There are 6 different choices for school B, 5 different choices for C. And here they just looked at this and they said 7 factorial, very similarly to the way that we said it. But yeah, so that brings us to permutation. So permutation is an ordered arrangement in which our objects are chosen from n different distinct objects so that r less than n. So that r less than n repetitions is not allowed. So the symbol NPR, n permuted r times, represents the number of permutations of r objects selected from n objects. So basically we have a total of n, so n different objects, and we're selecting r of them. So r objects. So r is always going to be less than whatever n is. Number of permutations of n distinct objects taken at r times. So the number of arrangements of r objects chosen from n objects in which the number n objects are distinct. Repetition of the objects is not allowed, and order is important, or order is important given by the formula. All right, so this is going to be the most important part for permutations. So given by the formula. So given by the formula, this right here is asking 7 choose 5, or 7 permuted 5 times. So basically, how many different ways can we permute 7 different things 5 times? So of this, we have 1, 2, 3, 4, 5. So 5 different slots. So here we would have 7 different possibilities, not 8. We would have 6 different possibilities here, 5, and so on and so forth. But here we're able to put it into a permutation and see what those values are. So again, permutation. So NPR is equal to N, sorry, what was it? Yeah, there we go. So N factorial divided by N minus R factorial. So in this case, for this problem, what we would look for, we could do this the long way. So 7 permuted 5 times. This is equal to 7 factorial divided by 7 minus 5 factorial. And we could expand this. So 7 factorial, or we could simplify first. 7 minus 5 is 2. So expanding the numerator until we get to the denominator, we have 7 times 6 times 5 times 4 times 3 times 2 factorial. So that way we know that it's being divided by 2 factorial. These two divide out perfectly. So what we end up with is 7 times 6 times 5 times 4 times 3. So taking this to Excel, what we have, 7 permuted 5 times. This is equal to 7 times 6 times 5 times 4 times 3. And that gives us 2,520. But there's also an easier way that we could do this one. So straight from up here, we could have said Excel, and we're looking for permutations. So permutation or permute. So number, here it's 7, number chosen is 5. And exact same values here. So here, instead of saying all of that, we could have said equal to permute. And here it's 7, 5. So N, R. So So let's try with this next one. So five permuted 5 times. So equal to permute. So 5 comma 5, and that is 120. And again, by hand, that's what they ended up getting. Cool, that's what we just got, those two. And perfect. So this, they're just showing us how to use it on a TI 84 Plus, like the fancy calculator. And this is how we use it on Excel. Look at that. Exact same thing that we did. So in how many ways can horses in a 10-horse race finish first, second, and third? So remember, permutation order matters. So all we have to do is out of the 10 horses, we need to permute them 3 times. So what is that value? So we could do it all by hand, or we could have Excel do the work for us. So 10 permuted 3 times. This is equal to permute 10 permute 3. And that's 170, or not 172, so 720. Simple as that. So 10 horses are distinct. Once a horse crosses the finish line, that horse will not use the finish line again. And in a race, finishing order is important. So because order does matter, we were using permutation. So I know I keep repeating that, but you guys will see that as soon as we talk about combinations instead of permutations. 720 different ways, exactly what we got over here. All right, ooh, perfect. Solving counting problems using combinations. So combination is a collection without regard to order in which R objects are chosen from n distinct objects, with R being greater than n, without repetition. So this is our key word for this one, without repetition. So things like this would be like a committee. So it doesn't matter if the person was chosen first for the committee or the person was chosen last for the committee. The committee is just formed with those people. Yeah. So here, Roger, Ken, Tom, and Jay are going golfing. They will randomly select teams of 2 players each. List all possible team combination. What is the list? Or that is, list all combinations of the 4 people, Roger, Ken, Tom, and Jay, taken 2 at a time. So what is 4 choose 2? So, all right, yeah, they did write them down. So let's write them down. So we first have, let's just use our first letter. So we'll use R, K, T, and J. So different samples of size 2. We have Roger and Ken. We have Roger and Tom, Roger and Jay. Then with Ken, we have Ken and Roger, which we already used. So Ken and Tom, Ken and Jay, and lastly we have Tom and Jay. Let's see. So did we get all of them? I'm not sure. Let's check. So we have 4 choose 2. And let's figure out what that value is. So 4 choose 2. So this is a combination. So equal to combin. So 4 choose 2, 6, and we have 1, 2, 3, 4, 5, 6. Perfect. So that's how we ended up with those numbers. So the list of all such teams, we said Roger, Ken, Ken, Tom, Roger, Tom, Roger, Jay, Ken, Jay, Tom, Jay. And 4 choose 2 ended up being 6. So there are 6 ways of forming teams of 2 from a group of 4 players. All right, so number of combinations of n distinct objects taken R at a time. So first, the n objects are distinct, which they are. Distinct just means like we're not looking at a bag of M&Ms where we have 5 red ones, 4 blue ones, and so on. 2, repetition of objects is not allowed. So no repetition of objects. So that's good too. 3, order is not important. So notice that it didn't matter that we chose Jay first or what was it, Kevin? Or Ken. It didn't matter that we chose Ken first or Tom. So those didn't matter. So now we're going to evaluate each of these. And I feel like we're pretty much experts at this now. So 4, choose 1. 6, choose 4. And we're looking at 6, choose 2. So if you guys wanted, you guys could pause the video right here and check them out yourselves. But if not, let's go ahead and take it over to Excel. Let's get a new sheet. Okay, so 4, choose 1. 4, choose 1. That's equal to, this is a combination, not a permutation. So 4, choose 1. Cool, we have 6, choose 4. So equal to combination 6, choose 4. And there's 15. So again, what this means is out of 6 different members, how could we arrange 4 to where order does not matter? So order does not matter. That's going to give us 15 different possibilities. Out of 6 different individuals, how could we arrange them in groups of 2 where order does not matter? Combination 6, choose 2. 15. Ooh, these kind of look really similar. So does that make sense? And answer here is, yeah, it does make sense because there's 4 or 15 different ways that we could arrange 6 people in groups of 4, or 6 individuals in groups of 2. So we would end up with 15 different distinct ways of selecting these numbers, 15 distinct ways of selecting these numbers. These are just the ways that we could arrange them without any order. So that's why they are similar. And let's see if we're correct. So 4, choose 1 is actually 4. 6, choose 4. So another way we could think of this, 4, choose 1. We only have 1 spot for different people. But if it were 4, choose, actually I like 4, choose 3, we would be missing 1 from each of those groups. So those 2 are exactly the same. So 6, choose 4 is the same as 6, choose 2 because they're we're looking at the stuff that's missing. So here we're missing 2, here we're missing 4, here we selected 4, here we selected 2. So that's how we ended up with those same groups. Same thing here. This is how we input it into our calculator. This is how we were inputting it into Excel right over here. And there we go. All right. So how many different simple random samples of size 4 can be obtained from a population whose size is 20? All right, back to statistics. How many different simple random samples of size 4 can be obtained from a population whose size is 20? So again, what we're looking at is a population with 20 individuals. So 20 of these. And we're looking at population of size 4. So each of these in here are of size 4. And there could be some in here. There could be some in this group from those 2 groups. So clear that out. So how many different simple random samples of size 4 can be obtained from a population whose size is 20? All right, big rule here. Does order matter? Does it matter that in our sample size, does it matter that we selected the first person first or the third person last? No, it doesn't really matter how we select these people. What does matter is if it's random. So in this case, it will be random. So total is 20. And we're looking at size of n equals 4. So here, what we could do is 20, choose 4 because order does not matter. And coming over here, 20, choose 4. This is equal to combination So combination of 20, and we're choosing 4. So there's 4,845 different ways of selecting those people. So use formula 2 with n equaling 20, r equaling 4. So 20, choose 4, perfect. And that's how we got that 4,845. So there are 4,845 different simple random samples of size 4 in a population whose size is 20. All right, solve counting problems involving permutations with no distinct items. Okay, so with no distinct items? Non-distinct items, there we go. So a DNA sequence consists of a series of 4 letters repeating representing a DNA strand that spells out the genetic code. There are 4 possible letters A, C, G, and T, each representing a specific nucleotide based in the DNA strand. How many distinguishable sequences can be formed using 2 A's, 2 C's, 3 G's, and 1 T? All right, so one more time, DNA sequence consists of a series of letters. They don't tell us the number. So there are 4 different possibilities. So we have A, C, C, this one's G, and T. How many distinguishable sequences can be formed using 2 A's, 2 C's, 3 G's, and 1 T? And I don't know, let's see. All right, so makes sense. So we have, so like 2 plus 2 plus 3 plus 1. So that's the number I was looking for. My brain kind of skipped and I forgot that we could just add those numbers. So 2 plus 2 is 4, plus 3 is 7, plus 1 is 8. So that's 8. So we have 8 different possibilities for these answers. So 1, 2, 3, 4, 5, 6, 7, and 8. So of these, we have 8 different sequences. So each sequence is formed. Each sequence formed will have 8 letters to construct each sequence. We need to fill the 8 positions with 8 letters. All right, so from here, what we could do is, let's kind of see what we had so far. So we had these, and again, what we're looking for is to for sure have 2 A's, to for sure have 2 G's, to for sure have 2 C's, and 3 G's, and 1 T. All right, so what we're gonna do is find, we have 8 different positions. So those 8 different positions. So we need to find where we could put A at. So we need to choose the 2 positions for A. And that would come with, so choosing for A. So we have 8 different positions to choose from. And we're placing that in 2, or we have 2 for those. So out of these 8 positions, we are choosing 2 where the A is going to go. So let's, for simplicity, let's just scratch out this one and this one. So now, actually backwards. So let's scratch out this one over here and this one. So now of those 8, 2 have been chosen. So that's where our 2 A's are going to be. So now for G, no, that's a C. So for C, we are going to choose 2 positions for C. So of the 8, we got 2 of them for A. So we have 6 to choose from, 6 left. And we're going to choose 2 positions for C. So from there, we chose, say, these two positions here. So that means we have 4 of them left. So now for the letter G, of the 4 remaining, we're going to choose 3 of them for the letter G. And lastly, for the letter T, we only have 1 left. So we have 1, 2, and 3. So for the letter T, we have 1, choose 1, because we only have 1 position left and we're, well, finding that right there. Okay, so with each of these, let's clear this out. So again, for A, we have 8, choose 2. For the letter C, we have 6, choose 2. For the letter G, we have 4, choose 3, because we wanted 3 Gs. And for the letter T, we have 1 space left and we're choosing 1 for that one. So multiplying all of these together, because we have all, like, we're multiplying these spaces together, we have, let's do a different color. So we have 8, choose 2 multiplied by 6, choose 2, and multiplying that by 4, choose 2, 4, choose 3, sorry, times 1, choose 1. So 8, choose 2, remember the, we could find each of these together and then multiply all of those products together. Or we could just expand it and see if it makes any difference here. So 8, choose 2, it's 8 factorial divided by 2 factorial times 8 minus 2 factorial. Actually, no, we're not going to do that. We'll just plug it into Excel and have Excel do everything for us. All right, so over here, let's get a new page. So illustrating everything that we have. So we needed 2 A's, we needed 2 C's, we needed 3 G's, and we needed 1 T. So for selecting so from those 8 positions, we had 8 places to choose an A or 2 A's. We had 6 places to choose 2 C's. We had 4 places to choose 3 T's and 1 place to choose 1 T. And now from here, this is going to be equal to combination. We're looking at 8, choose 2. Combination 6, choose 2. Combination, no. So combination 4, choose 3. And combination 1, choose 1. There we go. And now we're going to find the product of all of them. So selections, we have 28 times 15 times 4 times, well, not 4, but this one times 1. So 1,680. So there's 1,680 different ways to rearrange 2 A's, 2 C's, 3 G's, and 1 T. So let's see what they said. 8 different letters. Task, choose a position for the first 2 A's, then choose a position for the 2 C's, 3 G's, 1 T. And what they did here is they multiplied everything together. And then they started simplifying things out. So 6 divided out with 6, 4 divided out with 4, 1 divided out with 1. So we have this product right here. So they multiplied everything out, 1,680, exactly what we got over here. But that led us to this cool new rule. So the number of permutations of n objects of n, which n1 are of kind 1, and 2 are of kind 2, and k are of kind k. So this is given by the sum of all of them. So adding all of those numbers together, that's our numerator, times our denominator being our factorial. So n1 factorial, n2 factorial, all the way up to nk factorial. All right, so looking at this, how many different vertical arrangements are there of 10 flags if 5 are white, 3 are blue, and 2 are red? So we have 5 white, we have 3 blue, and we have 2 red. All right, so if we follow that formula, we have n factorial divided by n1 factorial, n2 factorial, and n3 factorial, because we only have those 3. So here, plugging all of that in, we have 5 plus 3 plus 2, and we're dividing that by 5 factorial, 3 factorial, and 2 factorial. Factorial there too. All right, so simplifying this, that would be 10 factorial over 5 factorial, 3 factorial, and 2 factorial. So we could expand it and see what we end up getting, or we could just keep it really organized and plug things in here. So looking at 10 factorial, what was it? 5 factorial, 3 factorial, and 2 factorial. So with 10 factorial, so this is equal to fact 10, 5 factorial equal to fact 5, 3 factorial equal to fact 3, and last one equal to fact 2. So now this right here ends up being equal to 10 factorial, and we're dividing that by, let's do parentheses, we're dividing it by 5 factorial times 3 factorial times 2 factorial. And they closed our parentheses out for us, but 2,520 ends up being the product of all of those. So there's 2,520 different ways to rearrange all of this. I'm sure they did it just a little bit differently by expanding everything out. Let's see. So let me show you really quickly. If you guys just want to enter it into Excel, that's totally fine, but we're going to see a different way of doing these. So let's clear this out. We had said 10 factorial over 5 factorial, 3 factorial, and 2 factorial. So 10 factorial, the largest denominator is going to be 5. So the largest one that we're going to expand out to is 5. So 10 times 9 times 8 times 7 times 6 times 5 factorial. And we have 5 factorial here, 3 factorial here, and 2 factorial. The reason why I extended out to the largest one is because we could just divide those out. If we expand all the way up to 2, we're just writing things a little crazily. All right, so now looking at that, we have 10 times 9 times 8 times 7 times 6. And let's expand the denominator out. So 3 factorial is 3 times 2 times 1. And 2 factorial is 2 times 1. So the ones end up dividing out on their own. And we have 6. 3 times 2 gives us 6. And lastly, 8 times is divisible by 2. It goes into that 4 times. And we're left with just this last product, 10 times 9 times 4 times 7. And let's see what that value is. So 10 times 9 times 4 times 7. Oh my God, it's 2,520, just like the other one. And that's it right there. So we could have done it this way, we could have done it this way, or you could have just straight plugged it in. It would have been a little bit sloppy, but you could have plugged it in directly into one of the cells there. All right, so here we seek the number of permutations of n, or n equaling 10 different objects, 5 which are 1, or 5 which are white, 3 which are blue, 2 which are red. Did that. They expanded and kind of simplified things out. They left it up to our imagination kind of, but we were able to work with that. All right, here we have a little bit of a summary. So combination, remember combination, what I want you guys to remember with combination, order does not matter. Does not matter. With permutations of distinct objects, permutations of distinct objects without replacement. Permutations, order does matter. So order matters. All right, so permutations of n distinct objects with replacement. So we're replacing everything. So AB is different from BA, and that's n to the power R. Permutations of distinct items without replacement. So these are different things. So try a bunch of different things. Everything is non-distinct. Permutations, non-distinct without replacement would be this value, the one that we just went over right now. And let's see this, compute probabilities involving permutations and combinations. All right, looking at this, in the Illinois lottery, an urn contains balls numbered 1 through 52 from an urn, or from this urn, 6 balls are randomly chosen without replacements. For a $1 bet, a player chooses 2 sets of 6 numbers. To win, all 6 numbers must match those chosen from the urn. The order in which the balls are picked does not matter. What is the probability of winning the lottery? All right, so probability of winning, let's kind of look at that. So probability of win is equal to 1 out of the total. So the total number of ways, or total number of plays. So total number of ways that you are playing. All right, so looking at 1, we only have 1 winner, right? So of the total ways to play, we have 52 different balls. So 52 different balls, and we're picking 6. So picking 6 different balls. All right, so our options are 52 choose 6 or 52 permute 6. So remember, choose are combinations versus permutations. Combination order does not matter. Permutation order matters. So does it need to be ordered or does it not need to be ordered? It does not need to be ordered because it doesn't matter if you choose ball number 5 first or ball number 23 first. Doesn't matter. You just have to make sure that those 6 balls end up being on your ticket. So we're going to use combination. Let's erase this really quick. So what we're looking at is the probability of winning is equal to the 1 winning ticket, and we're dividing that by 52, choose 6. So let's find that value really quick. So we're looking at 52, choose 6. And this is equal to a combination of 52, 6. And again, this is a different amount of ways that we could, so these are the different ways that we could select these numbers. So that is 1 over 203,58520. So there are over 20 million ways of selecting lottery numbers. So here they, I know you hear it's 1 in a million. Actually, it's not 1 in a million. It's 1 in over 20 million. So chances of winning the lottery are a lot smaller than what people are actually like saying out loud. All right, so now for that probability. So the probability of winning is the total number of ways that you could win, which there's only one way, and we're dividing it by the total number of ways possible. And oh, they actually did whatever this is called, scientific notation. So here, scientific notation, so e raised to the 0.8 to negative 0.8. What that tells us is that we're moving this decimal place over 8 spaces. So the actual probability of winning is equal to 0. We move that 8 spaces. That's 1, 2, 3, 4, 5, 6, 7, 4, 9, 1, 1. Or we could just say 4, 9. Or even better, we could say 5. Let's round up and say 5. So this is the probability of winning a lottery, or the lottery. And let's close this out. So let's see what they ended up saying. So here, the number of the sample space, so the number of ways that we could select, ended up being that 20 million number. And 2 ways. So each ticket has 2 chances of winning. Oh, shoot. I'm sorry, guys. I didn't read that part. All right. So for a dollar bet, a player chooses 2. Oh, I get it. I see. So there's 2 different sets of numbers. Well, I'm really sorry about this one. It isn't 1 out of that 2. So here our winning probability. We're moving this still 8 decimal places. So that's like if we were moving a 2, we would have 1, 2. So we would have 1 less of whatever number we had here. 1, 2, 3, 4, 5, 6, 7, 9, 8. Well, that's the value that we would end up having there. So there's 2 different ways. So there is about 1 in 10,000 or 10 million, sorry. So there is a 1 in 10 million chance of winning an Illinois lottery. All right, so a shipment of 120 fasteners that contain 4 defective fasteners was sent to a manufacturing plant. The plant's quality control manager randomly selects and inspects 5 fasteners. What is the probability that exactly 1 of the inspected fasteners is defective? So exactly 1, that makes me feel a little bit better. So a shipment of 120 fasteners contains 4 defective. Really quick before we continue. So 120 of 124 defective, that means that 116 are good. Okay, so the plant's quality control manager randomly selects and inspects 5 fasteners. So 5 inspected. So what is the probability that exactly one of the inspected fasteners is defective? So probability of exactly one defective. All right, so now probability of exactly one defective. Different colors. So probability of one defective of the 5. So the number of one defective of the 5 divided by the total possible, the total amount possible. All right, so exactly one defective out of the 5. So what we're looking for is 1 bad and 5 good. So up here, number of 1 bad and 5, or not 5, a total of 5. So 1 bad and 4 good. Divided by the total possible. So total possible is going to be out of the 120, we need 5. All right, so looking at this, so the probability of 1 bad is going to be 5 choose 1. And probability of 4 good, we have 116, and we're choosing 4 of those. And then for this bottom one, we're just looking at the total way that we could select them. So 120 out of 5. All right, let's look at these numbers. All right, so what we're looking for is 5 choose 1, or we're looking at the 1 good, or choose 1 bad. So this is going to be 120 choose 5. Nope, not 120. It would be 5 because we have 5 bad ones and we're choosing just 1. Now we're going to choose 4 good ones. And of the 116, we're choosing 4 of those. And total ways that we could choose all of them, it's going to be 120 choose 5 because we're choosing 5 of them. All right, so now this is equal to combination 5 choose 1. This is equal to another combination 116 choose 4. And lastly, the total would be combination 120 choose 5. 120 choose 5, 116 choose 4, 5 choose 1. All right, so now looking for that product. So probability of 1 defective, or exactly 1 defective, is going to be equal to this times this. So this times this, and we're dividing that by this, dividing it by this one. There we go. So the probability of choosing exactly 1 defective one, 0.18785, so 1879. And there we go. Let's see if we did this correctly. So the number of ways of choosing 1 defective fastener from the 4 defective fasteners. So really quick, it should be 4. So we have 4 defective fasteners. And okay, continuing. So the number of ways of choosing 1 defective fastener from 4 defective fasteners. So I, for some reason, thought that this was going to be, that this was 5, but it's actually 4 because we're choosing 1 bad one. We're choosing 1 bad one from the 4 bad ones that we have. And that's where this one came in. So the number of ways of choosing 4 non-defective fasteners from the 116, it's 116 choose 4. So of all the good ones, we're choosing 1 or 4 good ones. How many different ways of those are possible? So this ended up being the numerator. And lastly, the denominator, the one at the bottom, the denominator ended up being the different ways that we could choose all 120 of the fasteners 5 different times. And that's what they got there. They divided the 2 and got 0.1503, 0.1503 once we fix that little mistake. So the probability of randomly selecting exactly 1 defective fastener is 0.1503. So if we selected 5 fasteners 100 different times, we would expect about 15 of the samples to have exactly 1 defective fastener. And that sums up the last section that we're going over for this chapter. So if you guys do have any questions, please let me know. Please email me. But if not, good luck on your homework. Bye.